Hello, everyone. This is the lecture for section 2.1, areas between curves. So in the last couple of sections that we've been doing, and at the end of Calc 1, right, all we were learning how to do was take the area or find the area under a curve, right, from a section A to B, right? In this section, we're going to do the exact same thing, right? But now we're going to start talking about how to get areas between curves, okay? Um, It turns out that the sort of theory that's behind it is no different than what we've been building up to this point. Um, the theory that's behind this is still of Riemann sums. It's just a little bit of a difference here and there. But overall, it's still all the same stuff. So let me go ahead and get to that buildup. Okay, so suppose we have two functions. Suppose we have an f of x and a g of x, right? Where f of x is bigger than g of x. Okay. So what I'm going to do is I'm going to slap down an x and a y axis here. Okay. I'm going to grab that one, move it over a little bit. I'll grab this one and make it a little tinier, move it over. There we go. Okay. And I'm going to draw two. I'm going to draw two curves. I'm going to draw an f of x, right? I'm going to draw a g of x, and I'm purposely drawing them a little different, right? And g of x. Okay. And let's say we want a to b. We want the area between the two curves, right? So we want basically this little bit right here. We want all of this. Okay. This is what we're aiming for. We're wanting that little piece right there in the pink. Okay. So we're going to start off again using our definition of Riemann sums, right? So in this case, what we're going to do is both of the functions are going to be broken up over a common partition P, right? So each one of these are x of i's, right? A is x sub 0, and B is x of n, right? So this is x1, x2, dot, 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 dot. And we're going to get to I minus 1, x of I, okay? If you take a look, right, we're going to have two boxes here. I'm just going to draw them sort of off of one common box. And let's say this one goes about that high. Let's go ahead and do that one there. There we go. Okay. So in this case, right, we are looking for the area of this box right here, right? Okay. Now, we are dividing these up into regular partitions, right? So this right here, my delta x is going to be my b minus a over n, right? And the idea to find that little piece right here, right? This, the orange part right there, right? Is we're going to take the area of the big rectangle, right? Which is going to be defined by some f of xi, right? And then we're going to subtract away the area of the green rectangle that's right below it, right? Okay. And that one is defined by, right, some random gxi, right? So that's how we get the little yellow, the little orange box, right? That's how we get the area for the little orange box, right? So the area of the big one, right? The area for the area under the curve f is going to be given by this expression right here, right? And then the area under g will be given by the area given by this expression right here, right? So it's only sort of logical to say, well, we don't need the area for g, so we get rid of that one. We subtract that one away. That's how we get our region R. So this right here is going to be the area between the two curves. This is going to be our region R right here. Okay. That's how we find our area between two curves, right? And as we were doing before, right, since we're taking the limit as n goes to infinity and we have our a and our b, right, this translates to the expression that we have for the integral, okay? So the area between two curves is given by this integral statement right here, okay? Okay. The way that people usually remember it is there's a higher function and there's a lower function, right? Just find which one's the higher, which one's the lower, and you're off to the races, okay? So I want to go ahead and do an example for you all, okay? So this example has to do with two functions. So f of x is negative x minus 2 quantity squared plus 9, and g of x being 1/2 x plus 2. And we want to find the area between 1 and 3, okay? So I'm going to go ahead and do a split screen here so I can show you guys the two graphs, okay? Let me zoom out a little bit so I can get both graphs. There we go. So the first one, minus quantity x minus 2 squared plus 9. And the other one's going to be 1/2 x plus 2. There we go. And let me switch these out to just good old numbers. I was playing around with something before. There we go. Okay. And I'm going to go ahead and shrink this a little bit so we can all see what we're looking at. There we go. All right. So these are both of our functions. Okay. So we want something that goes, we want the area between 1 and 3. So we're looking at this piece right here. Okay, this piece right here. So what I'm going to do is I'm going to go ahead and make this a little smaller, and I'm going to go to the snipping tool. I'm going to grab that and sort of give us the picture of what we need, okay? And I'm going to stick that in our notes right next to this example, okay? Whenever my notes want to decide to work. Awesome. There we are, okay. So I've just gone ahead and thrown that picture of ours in our notes, okay? So let me zoom in on it really quick. We are looking for this area right here. So I'm going to highlight it in pink just like I did before. We want this little piece right here up to right there about. So this is what we're looking for, okay? Okay, so let me zoom out. Let me bring it back to our notes. Okay, so how do we find that area? Looking at our picture from over here, we see that the parabolic function, right? That's the top function. And then our line is the bottom function, right? So we have everything sort of sorted out already. So in order to find this, it's going to be the integral, right? We have our limits from 1 to 3 of the top function. So it's going to be the minus x plus minus 2 squared plus 9 minus the area of g of x, right? So minus 1/2 x plus 2, okay? I'm going to put that in big brackets to say that that is my integrand, and we're doing this according to the x variable, so dx, okay? Okay. If you expand this out, 1 to 3, if you expand out our integrand, you're going to get something that's going to look like this. And I sort of hope you guys do this on your own. It's to practice your algebra, right? It's going to be negative x squared plus 4x minus 4 plus 9 minus 1/2 x minus 2 dx. And if this cleans up, 1 to 3, if you clean all of this up, you get something along the lines of minus x squared plus 7/2 x plus 3 dx. Okay. Now we have it in a method that we can take the integral for, right? So the integral for negative x squared, that's going to be negative x cubed over 3, okay? Plus the integral for the 7/2 x is going to be 7 over 2 x squared over 2, multiplication in between. And then the integral for 3 is plus 3x. So this is our integral, and we need it evaluated from 1 to 3. Okay. So at this point, we go ahead and evaluate from the top one minus the bottom one. So it's going to be negative 3 cubed over 3 plus 7 over 2, 3 squared over 2 plus 3 times 3, okay, minus, I'm going to close that one off. I forgot to close that one. Let me close it off right. Minus, now the bottom one, right? So minus 1/3 plus 7 over 2 times 1 squared over 2 plus 3 times 1. So we have to evaluate each one of these separately, okay? And if you do so, you should get, and I'm going to like heavily reduce this a little bit, minus 9 plus 63 over 4 plus 9 plus 1/3 minus 7 over 4 minus 3. And if you reduce this all nice, if you actually plug this into a calculator, you should get something along the lines of 11.33 with a bar. Okay. Okay. So this is the answer. This is sort of like the work that goes behind doing the integral. Okay. I provide a QR code there so you can double check your calculations. So I'm going to show you guys how to do that really quick. I'm going to go ahead and do a split screen again. Let me find my Desmos. There we go. I'm going to go to the definite integral calculator. I'm going to go ahead and get rid of that. Come on. There we go. And delete. There we go. And I just get to plug in this thing directly. Okay. I'm going to plug in the exact integral that I'm talking about. This one right here. I'm going to plug in this, all of that. Right. And then I can move my limits around to what I need. Okay. So I'm going to go ahead and do negative x minus 2 quantity squared plus 9. Okay. Minus, and now I'm going to go ahead and do 1/2 x plus 2. I'm going to close that one off. So let me go ahead and move this into to the big screen so you guys can see what's happening. It's the top function minus the bottom function, right? Okay, and it's complaining about a parentheses. There we go. Okay, now this is not gonna, so this is not the picture in and of itself that you're trying to graph, right? It's not giving you the two graphs to find the region between the two curves, right? It's gonna just compute out the integral that you just found. It's gonna compute out the integral that you just found. Okay, so I'm gonna go ahead and do from 1 to 3. There we go, 11.33. So it's computing this integral right here, the one that I have in yellow. Okay, you guys can use this as much as you need to for your own work, including the online homework and including the quick checks and the lecture questions down below. Okay, so so long as you sort of use it to double check your work, don't make it a crutch. Okay, so long as you're using it to double check your work, that's perfectly fine. Okay. Okay, so that is how to find the area between curves. Okay, right after this is the very first quick check for this section. Okay, so go ahead, try these out. If you have problems, if you have trouble, come see me in the math lab. I'll try to be online at the same time. Or I have my Friday hours. Okay. All right. Moving on. For the problems that I provided above in your quick checks, if you graph them, you'll see an order already. Okay. As in, you can choose which one's supposed to be the top one and which one's supposed to be the bottom one. Correct. Not always do you have functions that set up that way. Okay. Sometimes the top function switches with the bottom function, and then it becomes the top function. Okay. So that's what I want to show you guys here. So let's go ahead and find the area between sine x and cosine x between 0 and pi. Okay. So I'm going to go ahead and open my Desmos calculator. I'm going to do a new one. I'm going to do a new graph. Uh-oh. Not what I wanted. I'm going to do a new graph. I'm going to do sine of x, and then I'm going to do cosine of x. Okay. So I'm going to zoom in here. And hopefully some of you guys already see the problem. And I need to do this between 0 and pi. So I'm going to switch my steps to pi over 4. So we get to see the divisions in pi there. Okay. So if you guys see, we want sine of x and cosine of x, the area between them, over 0 to pi. Right. So I'm going to go ahead and do another split screen. Notice what happens. The blue is our cosine function, and the red is our sine function, right? And if you guys can tell, they swap places at pi over 4. So if we want to find the area between these two curves, we need to take that into account, that at one point, right, cosine is no longer the top function, sine is the top function. Okay, we have to take that into account. Now, how would you do this? Sort of algebraically? The way that you would do that, right? Both of these graphs are intersecting at that point, right? They cross there. So the easiest way to go about that, right, is you find when sine of x is equal to cosine of x, right? If you remember from your trig class, right, we need to find whenever this happens. If you just look at your unit circle, whenever sine is equal to cosine, there's two spots that happens, right? In order for this to happen, x has to be pi over 4 and 5 pi over 4. Now, our interval states that we want it between 0 and pi. That's good news for us. That one doesn't count. So this one's the only one that does this. Okay. The other way that I've seen it done, I can go ahead and divide both sides by cosine. So I get something that looks like tangent of x is equal to 1. Okay. And that also just happens at pi over 4. Okay. So now to the calculus bit. We know that cosine is the top function up until pi over 4. And then after that, sine is the top function. Okay, so we need to keep that into account. And we write that out using our calculus. So let's go ahead and write out the integral that we're going to need to compute. So the way that this would be written out would be the integral from 0 to pi over 4. Let me make it a little bigger. Integral from 0 to pi over 4. So we said cosine was the top one, sine is the bottom one. So it's going to be cosine of x minus sine of x dx. That's going to be up to pi over 4. And now I want to do plus the integral. The new one now has sine up top, right? And cosine on the bottom. But it starts from pi over 4 and heads all the way over to pi. And now the integrand is going to be sine of x minus cosine of x dx. Okay, that is the split. That's how we appropriately split it. Now, if you look at all of these, right, we can split up our integrals a little bit. So it's going to be the integral from 0 to pi over 4 of cosine of x dx minus the integral from 0 to pi over 4 of sine of x dx plus the integral from pi over 4 to pi of sine of x dx minus the integral from pi over 4 to pi of cosine of x dx. So all I did was just basically split them up. And I can do that because they're integrals. Okay. Now we get the evaluation portion. Okay. In the evaluation portion, give me a second, being able to read my notes here. All right. So then when we evaluate, right, this is going to be equal to sine of x evaluated from 0 to pi over 4 minus plus cosine of x evaluated from 0 to pi over 4 minus cosine of x evaluated from pi over 4 to pi minus sine of x evaluated from pi over 4 to pi. So each one of these is the evaluation of the four integrals that I have up here. So this one is this one, right? This one is this one. This one is this one. And the very last one over here is this one right here. Okay. Now I can just go ahead and plug stuff in. If you do it right, I'm going to go ahead and, dole out the entire calculation. Root 2 over 2 minus 0 plus root 2 over 2 minus 1 minus a negative 1 minus root 2 over, whoops, let me do minus root 2 over 2 minus 0 minus root 2 over 2. So that's each one of the computations from the section above it, right? If you work this out right, you get 4 times root 2 over 2, which is equal to 2 root 2. And if you plug that into your calculator, you should get something along the lines of 2.82 and some change. Okay, now let's go ahead and make sure that this is the case. Okay, again, I'm going to go back to my Desmos calculator that I provided you all, definite integral calculator. This time around, I have to split them up because there is a split. I can't create one entire integral to compute everything. So I'm going to do, I'm going to go back over here. I'm going to make my splits, my steps into pi over 4s. So I can see all my, since I'm working with trig functions here, okay? I'm going to go ahead and sort of delete all of that. I'm going to go ahead and put my my functions in. So from 0 to pi over 4, right? That's cosine of x minus sine of x. So I'm going to do cosine of x minus sine of x, okay? And I need it from 0 to 4. So I'm going to change this to 0, or pi over 4. And I'm going to change this to pi divided by 4. And it gives me an integral. It gives me an answer there. That answer being point, oh, let me do a split screen. There we go, 0.4141. Okay, and now I get to do the exact same thing But now I need to put in the other one. So this is, whoa, undo. Now I'm going to do the exact same thing, but I'm going to basically change the order, right? So it's going to be sine of x minus cosine of x. Okay, and this one's got to have to be from pi over 4 to pi. So I'm going to do pi over 4 here, pi divided by 4, and then b is going to be my pi, right? So I'm going to do pi. Okay, and the answer I get for that one is 2.4142, right? So plus 2.4142. And if you add those two together, right, I'm going to go ahead and do it just right below here. 0.41421 plus 2.4142, 2.82841. So 2.82841. Okay. Now, that's all great, but I'm hoping that it is 2 root 2. So let's go ahead and compute that value. So 2 times the square root of 2 gets us our 2.82 and change. So the actual answer, right, with no approximation would be the 2 times the root 2. Okay, if we need to approximate it, it'd be my 2.8284 and change. Okay. Again, you know, use the calculator to double check your work. Don't use it as a crutch. Okay. So after this, what I'm going to do here is just like how we were doing areas between curves um, based on the x variable, right? We have expressions that do the exact same thing for areas under the curve when the variable, the independent variable is your y variable, okay? And this is exactly how you would think it would go. So again, I'm going to go ahead and put down some x and some y axes here. There's my y-axis, and here's my x-axis. Okay. And I'm going to put down two curves where the independent variable is the y variable. So that's basically something that runs downward like this. All right, I'm going to do another one over here. Okay, so this one's going to be my v of y, right? And this one's going to be my u of y. Okay, those are our two sort of functions. They're basically going up and down instead of left and right, right? Okay. Then the region between the two curves, let's say I wanted them between an A and a B, right? So I want this area right here. None of the theory changes really. I want all of this. I want all of this area right here. I want all of this. Okay. Then that region R is given by u of y. Oh, I have them backwards. Isn't that great? It's supposed to be v of y minus u of y. I will make the change in that's my bad, that's a typo. Big old typo. Okay. So it's the same sort of theory. That's going to be my R region. Okay. You still are thinking in terms of, the high function and the low function. Okay. Um, but the theory, like I said, doesn't change. Okay. Uh, now, let me go ahead and move on to the example. Unfortunately, our calculator won't be able to compute, it won't be able to do the integral, right? Uh, it won't be able to, it won't show you what you're computing at least, right? But you can still graph the two things and see what it is that's going to be graphed, or what it is that you're going to be looking for. So I'm going to go ahead and open up another Desmos here. I'm going to put the two functions in. It's going to be x is equal to y squared. Let me make the lines thick. There we go. And y is equal to x minus 2. So let me zoom in on that. And we want it from -1 to 2. And these are y variables. You guys notice that. So y variables. Okay. So we know what region we're actually looking for. We're looking at this region right here. So I'm going to go ahead and minimize this. I'm going to take a picture of that. I'm going to go ahead and do bam. There we go. Zoom out a little bit. I'm going to put it down there. Okay, so we know what we're looking for. We are looking for this piece right here. That right there. Okay. Well, like I said, none of the theory changes, right? If we're looking at this, picture in terms of the y variable being the independent variable, right? Then we can see the line is the top function, right? And the parabola is going to be the bottom function. Okay. So that's all that changes, really. Let me go ahead and center this nicer. There we go. So the problem is this. Okay. We need everything in terms of the y variable. Okay. So we need x in terms of y, right? Not y in terms of x. That's what we were comfortable with before, y in terms of x. But now we need to flip them. We need x in terms of y. This is okay. This one needs to flip. Okay, so I need x is equal to stuff in this case. So I'm going to start minus 2. Okay, so here's our start. I need to get the x by itself this time around, right? So I can just go ahead and get the -2 and +2 plus 2. So x is equal to y plus 2. This is our top function that we're going to use. So we are no longer going to be using this one. We're going to be using this one in our calculations. Okay. At this point, none of the math changes. Okay. We know what the bottom function is. We know what the top function is. We know from where to where we need to go. So the expression that we're going to write down, the calculus that we need to solve for, is going to be the integral from -1 to 2 of the top function, which is y plus 2, okay, minus the bottom function, which is y squared, okay? And hopefully you guys have been taking the previous warning that I had to heart. We are doing this now dy, as in we are the variable of integration that we're going to be using here is the y variable, not the x variable. So we're going up and down rather than side to side in this case. So from here, so I'm going to put this all under one integral. So integral -1 to 2. I'm going to keep the order. Y plus 2 minus y squared dy. And if you guys were paying attention in the last couple sections, remember how I said to start writing out your dy, right? Because in this case, our variable of integration is the y, right? And if you integrate this appropriately, you're going to get y squared over 2 plus 2y minus y cubed over 3 evaluated from -1 to 2. Okay. And if you go ahead and plug this in, I'm going to go ahead and evaluate here so you guys can follow along. 2 plus 4 minus 8/3 minus 1/2 minus 2 plus 1/3, right? And if you compute this all out appropriately, you should get 4.5. Now, the Desmos calculator won't work for something like this. It won't give you, it at least won't give you the correct picture, but it will give you the correct computation. So what I'm saying here is this, that because of how it's graphed, because of this being the actual graph of the expressions that we're playing with, right? Desmos can't compute it, right? It won't give you the computation and the picture correctly at the same time, okay? But what it will do is it will compute this thing for you. And that is exactly what we're going to do, okay? So I'm going to go ahead and do a split screen here. Hopefully what I'm saying is making sense here. I'm going to go back to my definite integral calculator. Let me close a couple of these. Just leave that. Bye-bye. Bye-bye. I'm going to go ahead and open my definite integral calculator again. I get to give this thing my my integrand, right? And it'll give me the computation for it. So in this case, see how I have it down as y's? That's okay. I'm going to go ahead and switch it to x's just so I can see what my computation is supposed to be. So I'm going to go ahead and do y plus 2 minus y squared. Oops. Look at me go. X plus 2 minus x squared. There we go. Okay. And I need it from -1 to 2. So notice what's happening here, right? It's not giving me the right picture. It's not giving me the two curves that I want, right? But it is computing the area between the two curves and it's giving me the correct answer. Okay. Hopefully you guys see what I'm talking about here now. So this is only going to sort of compute it for you, right? It may not give you the right picture for it. So you still have to do a little bit of thinking there. Okay. Okay. After this, it's your quick checks. Okay, go ahead and try these out. These are a little harder since we're going up and down rather than left to right. Okay, and after this, it's lecture questions. Okay, if there are any questions, if you guys get stuck on any one of the quick checks or the lecture questions themselves, I'm in the math lab at the in the math building. Like I said, I'll be try to be online during those lab hours or during those office hours, and then I have Friday hours as well if you guys want to come in during that time on Zoom. Okay. Besides that, I'm all done here. Happy studying.